On this episode of Pipeline Things, we continue our discussions on PPIM. We talk about, I want to ask you, how would you define the word permanent? Before you jump in this episode, maybe hit pause and think about that for about 30 seconds before you hear the answer that we give you as we talk to a return guest on that subject. What is permanent? Welcome to this edition of Pipeline Things. We bring on a return guest. Super excited to talk to him. But Chris, before we get into this,
I just want to say something first, though. This is your show, by the way.
I know it's my show.
I need you to know that.
I know this.
Like, you are the host, and I am only the co-host.
I have a question. Was that called into question somehow that I need to be aware of?
When you're in a relationship, sometimes you just have to be supportive and affirming of your partner. And I'm just letting you know, this is your show, bro.
I appreciate that. If it's ever called into question, we have a different problem.
All right, I got you back.
Now that we've done that, I remember when I came into this industry. Some of you guys may know this out there in the audience. I actually worked in the deep water offshore platforms, right? And what was really funny is we were working on a lot of the platforms, like the earlier deep water free floating ones, not the standing ones. I'm talking about the floaters out there. Actually came about in like the mid and late 90s. And just out of curiosity, it very much relates to today's episode. How long do you think they designed those free floating deep water platforms to last? By free floating, I mean it's moored to the seafloor, not directly like a jack up, before anybody takes issue with what I said. Come on.
It depends.
Oh, no, it doesn't depend. They had a design life. And I'm asking you what you think the design life was.
I'm going to arbitrarily pick something.
Okay, do it.
I'm going to say...
Good Lord.
15 years.
Oh, you're close. It was 20. Almost all of them were designed for a 20-year design life. So you can add, right? I mean, 1995, what happens at around 2015?
Yeah, you're at
design life.
You're at estimated design life.
So
that's what I would leave everything with, estimated.
It's really funny.
I could have been wrong back then.
Right. So what was really comical is all these platforms started reaching their design life in the early 2000s. The oil companies weren't like, hey, let me take this multi-million-dollar platform and just rein it in. Its life is done.
Hey, refineries do? They just do a turnaround. Why don't they just do like turnaround, like find critical parts and just replace those?
They started a program on life extension of offshore platforms to figure out how do we use these for longer than we originally designed them. And it's just comical because I think, I wonder 20 years ago when they set 20 years down, if they envisioned kind of the discussion that it would create, exactly 20 years down the road. Now, what's funny about offshore platforms, for those of you who know, is most of them are designed with a safety factor of 10. So they actually have a quote-unquote life of 200
years.
So what do you think the first suggestion was? Well, let's just go down to 9.
Why don't they cut it in half?
It made me laugh. And I remember being a part of those very early life extension questions
that's funny.
On offshore platforms. And I was actually well into midstream by that time. But I remember laughing. Thinking,
you're welcome, by the way.
Yeah, I know. Thank you so much. It wasn't just you, though. But it relates to today's question because we're going to be talking about this subject of permanency. And when we would design something, I feel like any time that you put a life on it and you say that this thing needs to last this long in the context of pipelines, I would put $100 on it. We will be talking about that life at the time that ends because we'll need more from it than you
100.
put. Right, especially with the age of our pipelines. So anyway, fun story. So I'm going to go ahead and bring on the guest.
I thought you were going to ask what we thought, because we kind of talked about this the last time we spoke to this guest, was what do we think the design life was for pipelines that were built 60 years ago?
No, I'm fairly certain he made that up, but it was still a good answer. So.
But yeah, it's going to be fun.
It is.
You know what else is fun? And
what?
I'm sorry, I'm going to do this for us Houstonians. What's around the corner, brother?
Mardi Gras?
Rodeo.
Oh, rodeo.
Yeah,
yes.
rodeo is always a good time. So I don't know. I just like bringing that up for all you Houstonians. Check out, enjoy. For our guest, I'm very curious if he's been to one of our local rodeos and if he has a fun
I don't know.
story
Let's bring
about
him on. So Tim Malley with Hinkle, CSNRI, is joining us again today. And the subject for the audience is the PPIM paper he wrote, which is the case for the permanency, love it, permanency of composites, testing analysis, and a case study. But before we get into your paper, the first question, Tim, that you must now address is, have you been to the Houston Livestock Show and Rodeo?
I have been to the barbecue cook-off.
Okay.
And that's about it. Two
Hey.
times. One, I was a privileged, guest getting the access to some tent that I can't even remember whose tent it was, and lots of great barbecue, lots of drinks being passed around.
So I just recently learned this. You used to live in Houston though, right?
I did, yeah, for 3 years.
Shame on you.
For real, you didn't go to like any concerts, nothing.
Never went to a concert, and then I did try doing the cook-off outside of the private venues,
That's not
where
fun.
we were.
No.
Yes, we were herded like livestock through this very generic, bland barbecue line, and it was not a great experience. Don't recommend that side.
I'm sorry that you have not been to the HSLR. That's disappointing. Yeah. So.
And it's not just the concerts. Like the problem is like they recently dropped the lineup, and for me again, it's all about expectations, And I think to me it ties a little bit to like permanency. Like I'm kind of a permanent rodeo goer here for Houston, right? And every year we're evaluating the rodeo, right, and saying, oh, is it going to be good or bad? And it's super subjective to a lot of times people saying it's all about the lineup. Oh, like how was the lineup? How was the lineup? Oh, the lineup was fire. The lineup was mid. And I'm like, yeah, but the rodeo too, guys. That's what it's about, So, anyways, shout out to HLSR. Shout out to everybody that's going to the rodeo. Love to hear some stories if you bump into us.
All right. So, back on point. Your topic. The permanency of composites. Let's just start with that word. Tim, what is permanent?
As Chris said, it depends.
Wow. So I assume you took it was, look, it's how the paper opened. Like you literally asked the question in your paper. I don't have to read it, but you said, what does permanent truly mean?
Permanent means forever. No, permanent means forever. I'm drawing a line in the sand. When you say it's permanent, it's permanent. And the only way I think that would change is if something it's permanent. Or unless it dies, right? I was going to try to turn to something organic, but it's permanent. It's forever. That's what it is, Tim.
So you're telling me that our pipelines and our non-composite repair methods are all permanent, right?
They will never die. I mean, it's a valid point. Go ahead.
I do want to expand on it because I think if you asked 10 different people, you'd get 10 different answers on what they thought permanent would be.
Yeah.
And so
Tim,
at the end of the day,
I'm sorry, I'm going to interrupt you. You're not going to get momentum. Make that a PPI paper next year. Like,
how long
was that
permanent?
a poll on
a
permanency?
poll on your customers. So over the next couple of months, talk to people, write it down, poll it, and just share the results on what did people think permanent meant.
Cool.
That's a great idea.
Have fun with it.
I'm going to do it. Yeah. Well, I will. Yeah, but at the end of the day, what are we going to be graded on as operators? I mean, obviously, we want to do what's the best thing for the pipeline to extend its life as much as possible. Sometimes the economics, I mean, we talked about this in the last episode. Every ditch is like a box of chocolates.
Yeah.
Sometimes there's going to be reasons why you can't fit those repair methods into what you're looking at in your ditch. So with a composite, we have to start at somewhere where the government in the past has had a little bit of say on it. So when the current 192 and 195 language on alternative repair methods was written, there was a docket that was published along with it. So if you have the paper, it's a lot of letters and numbers that tell you which docket it is, published in 1998. But essentially that docket says that it wants an alternative repair method to last longer than the remaining life of the asset. And so there's a lot of ways that you can do that. I mean, kind of going back to that design life question, 50 years is how a lot of pipelines got designed for, but that's not the service life. Like they're still in service beyond that 50-year life, just like the offshore platforms. So at that point, it does become a somewhat subjective discussion of what's your asset. I mean, there's a lot of operators out there currently looking at their remaining asset life, looking at the anomalies in their asset, how their pipe is cycling, what are the operating and maintenance conditions on that pipeline, and they may only have 10 years left.
Yeah.
So at that point, a composite being put on that pipeline really only has to last 11 for the sake of argument.
So it's interesting.
But
so,
I know I know I'm lobbing a grenade into the studio to
no, it's great.
see where you guys want to unpack that.
That docket you're referencing, for everybody to know, was RSPA 98-4733, and you actually quote. I think this might be my favorite definition of permanent. It says a repair is permanent if it's expected to last as long as the pipe under normal operating and maintenance conditions. Right now, I love the qualifiers: normal operating, normal maintenance. All of that makes sense, and I do think it says a stage. We expect it to last. I think that actually sums up operators' expectations, if I'm being real. So if you ask that question, what I don't like about it is you might get 10 years, you might get 25 years, you might get 50. The reality is I expect it to last as long as my pipeline is going to be in service in order for that to be permanent, which, if it's a gathering line, might be 10 years. That might be the service life on that. If it's a natural gas transmission line that we have difficulty replacing, it might be, near perpetuity. Might be 100 years. Could be anything, right?
Mm-hmm.
But it will vary among pipelines, and there's definitely not a singular answer. So, all right. So let's get right into it then. If the definition of permanency is that it must last as long as a pipeline, then Tim, what are the issues that make composites non-permanent?
Yeah, there are several issues. Where I kind of took it in the paper was to divide it into a couple things that you want to take a look at when you're looking at how a composite performs in the long term. The first thing that comes to mind is long-term strength. So that long-term strength is a function of the composite losing its strength under time under certain loads. That doesn't mean it will always lose its strength. That means that if you put too much stress into not enough composite, it will eventually lose that strength. So there's a big testing program that's recommended for composites. You can do that either 1,000 hours or at 10,000 hours. 1,000-hour testing is obviously not permanent. 10,000 hours is closer to permanent than 1,000 hours is. But what the 10,000-hour test allows you to do is you have to have 18 plus data points. You're forcing failures at certain stress loads, and that will create a linear regression curve that allows you to understand where your composite strength is going to be at a worst case scenario at 50, 100 plus years down the road. So when you have that strength mechanism accounted for in your engineering design plus safety factor, it kind of goes into the case study that was presented in the paper. You may never and probably will never initiate that creep degradation mechanism as far as the strength component is.
Let me interrupt you because I want to repeat it for the audience, because the audience probably hears somebody told me once that I'm going to have trouble following all the technical stuff on your show. And so I think this is an area where we might have some people that don't follow it as well. So composites, right? They are a combination of some type of a binder and then a filler material, if you will, which is typically glass of some sort, or it can be carbon. And then your binder is like an epoxy or a water-activated epoxy, right? So the degradation mechanism that you were describing occurs because that epoxy material will tend to lose strength over time. So in simple form, if I created an epoxy bar, if you will, and just hung a dead static weight from it, that wouldn't last until perpetuity. At some point, it would stretch and snap if the load is high enough over time to instigate a creep mechanism, right? And that could be, depending on the magnitude of the load, will then influence how fast that creep mechanism happens, how fast that degradation happens.
Correct.
So you guys have two tests that take care of this: 1,000 hour, which isn't very long, and a 10,000. But even 10,000 hours is not very long, Tim. So these tests have got to be simulated in some fashion, right? They're intending they conducted at like elevated temperatures to simulate, right, an accelerated life. Okay,
that's right. Yep.
Got you.
Yeah, the temperature will influence how the composite performs in those various elements of stress.
Right. And so to get from the audience, I want them to understand this. When you properly design a composite, not just grab it off the shelf, you start with a composite and you say, hey, as long as my load is below this value, the creep mechanism should not initiate. And then you seek to design it such that you never get above that mechanism. Is that how I understand it?
Correct. Yep. With safety factor.
With a safety factor. So if creep,
and just to correct something really quick.
Correct.
Sorry.
Don't apologize.
I'm
You're
not
Canadian.
well,
Wait,
I'm not
am I
trying to-
wrong?
Canadian.
No,
Don't
I'm not trying to
apologize.
take over the show like I did last time, which I apologize for that too. But but the fibers are the load carrying mechanism. I believe you said epoxy. I just wanted to correct that really fast because the
thank you.
epoxy is the more temperature limiting factor. The epoxy is what's going to degrade, especially
Right.
depending on how it's selected. There's a lot of different epoxies out there.
But then it can't load share as it breaks down. Fair enough, right? So the epoxy
Exactly.
permits the load
So-
sharing amongst fibers. Got it.
So the epoxy will affect the resin, but the stress that you're putting the composite under will be a component of the fiber you select and the stress amount that you're putting into the composite at that point in time.
Thank you. So just so that the audience understands, you get from this regression curve, you say that, hey, creep would start at a load of 100, for instance. In the pipeline, you're going to make sure that the composite isn't loaded to 100. It might only be loaded to some safety factor below that, maybe 75, maybe 50, which I want the audience to understand should ensure that the creep mechanism is never activated, which should ensure that the long-term strength of the composite is never reached if it's designed properly, which means in theory it should last as long as the pipe that it's put on.
Right. From a strength mechanism.
From a
Yes,
strength
correct.
mechanism. All right, give me the next mechanism. So that's one degradation mechanism. Is there another?
Another degradation mechanism is cyclic fatigue, which kind of has a lot of different components taken into it for composites in general. The overall system repairing the pipeline. So if we're looking back to what the code says or the docket even in reference to how the code was written, it says it has to last as long as the asset under normal operating and maintenance conditions. So part of that operating condition is cyclic fatigue. So for liquids lines that have aggressive cycling, that's going to be a lot different than a natural gas line that is very light in its cycling. We still would want to take a look at how the composite acts under both of those services, but your aggressive cyclic fatigue can have, as we talked about last time, the essential variable of installation pressure as a concern, because when you have pressure in the pipe, you're going to have a bonding mechanism, which is another thing I wanted to bring up, to make sure that your composite is adhered below that pressure at installation, which then brings in, installation quality, having a good surface profile before you install the composite. But there are analyses that you can do, and then you combine those with the testing that was done to be able to verify what the remaining cyclic fatigue life of the composite reinforcement over the specified anomaly can achieve.
Right. But so I want to set this for the audience. So you've got a cyclic fatigue mechanism. If it's active on your pipeline, the composite won't eliminate all of the stresses that might act 100% on that fatigue mechanism, which means that fatigue is still quote unquote possible. But that's a pipe problem. I mean,
Yeah.
it's a composite design problem, but that's not necessarily, I mean, as you described it, I'm like, that's not a degradation of the composite mechanism. That's just an appropriate design. But further to that fact, in that regard, steel sleeves are not permanent. I mean, steel sleeves don't eliminate cyclic loads. And so, especially, I mean, if they're installed improperly, then the annulus just fills, and then the annulus pressure cycles, and the fillet weld on the outside fails, right?
Yeah.
So I just want to make sure I'm not missing anything. There's not an actual, or I mean, beyond the bonding, the lap shear, I guess you're right. That's what you were referring to, right? So if you don't install the composite at zero pressure, if you installed it at something higher than zero pressure, then conceivably there is a breakdown between that the bonding mechanism, which would provide reinforcement below the installation pressure. Is that correct?
There can be, but ultimately where we have seen the testing fail is a breakdown in to your point, the stress amplitude of each cycle gets reduced by the composite.
Correct.
So if we're looking at reinforcing a crack-like defect, for example, just because you've got that sharp tip and each unreinforced, that tip is going to open with each cycle a little bit more. That's where Paris law and the delta K portion of that comes from. But when you put the composite to reinforce that, you're going to reduce the amount of opening of that tip, the stress amplitude with each cycle, and you're going to prolong the cyclic life of that particular anomaly.
I agree. Okay. I got it. I understand that.
So sorry, I need to take that through to to the end of the thought. The end of the thought to answer that question though is, at some point that stress amplitude will happen so many times that that defect will go through wall.
Yeah,
The
absolutely.
point of the composite is just to push that so far into the future that it's not going to be an issue during the life of the asset.
Right. And I guess that's where my comparison to steel sleeves comes in, right? Like steel sleeves can only push it out there too, like so far in much the same way. And then they even have their own design life in that regard. But it's just interesting to me that we don't consider that, right? Like nobody
Yeah.
asks what's the design. I mean, Chris, have you ever heard anybody ask what the design life of a steel sleeve is? I don't think I've ever. I think they're just considered permanent by the
I don't know
industry.
if it's been that intentional,
Yeah.
where somebody was like, "Hey, are we sure we are doing this right?" Like, I don't think we had a very specific effort. Now, that doesn't mean that there hasn't been some study out there. Like, we don't.
Yeah, Fudge
have-
did one. We talked with Fudge
yeah,
about it.
But I also mean, like, we don't have like all of the PRCI work, archived in our mind. So there might be something out there that we're not aware of. But it's normally not a mainstream effort that's done as part of what we would call O&M, and then either on top of or adjacent to O&M integrity management.
And I'm not here to shoot holes in any other repair methodologies.
No, we can. Let's go.
But
Let's get them all. Let's line them up. Let's start with steel sleeves. Go down the line.
Like I told you, I'm a mediator,
No, no, no.
more
It's
than anything. But what I do want to provide is that when that an engineering analysis component of the CFR requirement in 192 and 195 is met, you should have at least a minimum consistently conservative value in terms of remaining composite life that you get for this repair area. And that will at least help you to make an informed integrity decision of, is this, in my opinion, a permanent repair or not?
Yep, gotcha. All right. Hey, we're going to take a quick break, Tim, and our audience. When we come back, I want to talk about what needs to happen in order to ensure the composite repair is permanent. And you do a good job of describing that in the paper. So, audience, hang on, and we're going to be right back. All right, welcome back as we continue our study with Tim Malley. So, Tim, you did a good job, and I just want to reiterate from the audience. We started with that definition of permanency, and then you did a good job walking us through, and there was reasons why I did that for the audience. How did we even start with a justification for how composites are permanent,
How
right?
they
And
qualified?
how do you qualify them as permanent,
Is
right?
it a
Through the testing.
qualified material
100%.
repair method?
Right.
And it's in code. We were struggling with how do you define permanent.
Yep.
You alley-ooped it.
Yep.
Good job.
Again, it's all around you design it properly. You should never hit that creep mechanism. Therefore, it should be permanent. You assess that flaw appropriately. You make sure that it has sufficient life, whatever you define that as, to be permanent. Love it. Where I want to go now is I want to talk about, because I thought the paper did, honestly, I thought it did a really good job laying out.
Did we run that through like an AI checker to see what percent of this was AI written?
We did.
That'd be fun. We should
I can confirm it's 0% AI written.
I was going to make a
6,000
statement.
words, all from out of here.
From the dome. Hey,
So-
at least you're smiling about that. You didn't get offended that I asked.
Yeah.
I think about that way too much these days.
What advice or where do you recommend that operators start? So let's start with the operator who's looking to use a composite repair, maybe for the first time on a defect or maybe for the first time ever. Where should that operator start
Yeah, I think the operator
to make sure they
needs
get a
to start-
permanent repair? Let me qualify it. To make sure they get a permanent repair.
Correct. Yeah. Yeah, I think the operator needs to start with what the code says. And the code is going to say you have to have an alternative repair method that through reliable engineering tests and analyses shows you can permanently restore the serviceability of the pipe. So there's that nice word permanent in there. But kind of the two other big things that I take out of that is tests and analyses. So the operator will need to understand how the composite has been tested. And there's a couple different ways to look at that. There's the material testing. So to the earlier point of a composite is multiple materials being put together to get a new material, and you get the performance traits of that new material. You need to understand what that new material is. So if you're using a carbon fiber and epoxy, you have certain strength and adhesion and flexural modulus, and then you need load transfer compression. So you want to do, that's where the long-term strength testing takes place. That's on a material level. And then once you take care of looking at that, ASME PCC2 gives you a great starting place to look at the material properties of a composite. But then I think there needs to be some education in general of, for testing, you need to also look at the full scale performance of how does this particular material interact with certain integrity threats now.
So let's make this real, Tim. Because I actually got this question twice, believe it or not, at this past PPIM. Somebody walked up to me and they said, Rhett, how do you feel about the installation of composites on a buckle in a geohazard area? Go, Tim. Because I know in the paper you address dents. That's easy. We've been doing that forever. Corrosion, I think there's plenty out there. If an operator came to you and called you up and said, ding, 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 Mr. Malley, I have a buckle in the field and it's in a geohazard area that I know is active. Can I use your composite? What's your answer? Click.
How soon do you need to address this buckle?
Right. But why do you ask that? Why do you say, how soon do you need to address that buckle?
Because for a buckle,
and for the audience, I'm intentionally choosing a non-standard defect. If I had thrown corrosion at Tim, he would have an answer. If I'd thrown dents at Tim, he would have an answer. I am throwing something at Tim that I know is non-standard application.
Yeah, absolutely. And so for a buckle, it's the root cause is that it's being created by some sort of operational stress. And because of the buckle, it's going to be from an axial type of concern. If this one, for instance, is coming in a geohazard zone, that's likely the root cause. A lot of the testing that has been done on composites so far for axial loading has taken a look at how does a composite perform in bending, and then how does it perform in axial tension. So really you would want to take a look in that moment of how is the geohazard coming at the particular buckle. So is it going to be a bending concern, an axial tension concern, a combination of both?
And then is the testing adequate?
Exactly. Yep.
Yeah, that's great.
So for some of the wrinkles, which were created during construction that composites have been tested on, there wasn't necessarily a bend to failure performed on those wrinkles, because the primary concern for wrinkles were the freeze thaw, the different level of pipeline support. Has the wrinkle been disturbed? Did the backfill and compaction happen? So there was a bending cycling regime that was conducted on a wrinkle. And then just taking a look at if the wrinkle is unreinforced and reinforced, what's the extra amount of bending cycling you can get. But that, when you're looking at a buckle that's been, there's a certain amount of stress that's in the buckle, you would need to have a significant amount of axial reinforcement added through the composite fibers. And that's what you would want to take a look at through your testing that's been completed and your analysis.
Yeah. So for the audience, where I wanted you to get was on the testing and analysis. Like for that type of threat, it's not any composite anytime. It's you really need to make sure that the testing and analysis adequately addresses that.
I would bet a big audience of ours is still very much focused on the integrity management side. And this is very much what we preach about when you use ILI. Right? Is when an ILI specification is set, it's usually based on some kind of small and full scale testing. And a lot of times we'll see claims on LinkedIn as to what these tools can or can't do. But if those aren't translated into the performance specification, that's where we try to create awareness and say, understand the spec, and if what they're saying they can do is in the spec. Because if it's not in the spec, then it could be based on a case study, which is not necessarily compliant with 1163. That ports over here the same way, right? Is it's instead of it pointing to a RP or standard on how to qualify a repair method using composites for a specific threat in a specific scenario, they just left it simple and said it's based on testing and analysis. And so in this case, that's kind of what we're getting, is it's just understand how each composite has been testing, and if the scenario that you're looking for is included in that testing analysis. And that's kind of the jump. That's how you start. And if there's nothing off the shelf, then you hope that you have a vendor out there that can do this pretty quickly based on whatever extended life, right? Or whether it's temporary or permanent that you're looking for.
So the next subject in the paper that you went to, and I want to make sure we go here, is you give some guidelines for evaluating existing composite repairs for permanency. Right. So I'm going to set the stage. I'm going to change it. Now we're going to role play a little differently. I'm somebody who, maybe I bought an asset. Maybe that's a good way. I bought an asset and just found out it has 100 composite repairs on it. I have limited documentation on it. What advice do you give that operator for evaluating the permanency of those repairs? Where does somebody begin with that?
Does this operator have any access to potential design records, or is it just
So go ahead and ask me the question. Oh, yes.
Composite agnostic.
There you go. So no, so you asked the question. I went and looked into my system. Unfortunately, I had a properly trained AI. And the AI responds back and proceeds to give me a list of the design documents. So now I have these great design documents. Check.
Excellent.
Right. So it looks like,
Great news.
you know, it looks like I installed some Atlas system over my corrosion.
All right.
Oh, we're going product specific now.
Yeah, I was throwing him a bone,
Oh,
right?
man.
Looks like I installed an Atlas system all over all these corrosion defects. Am I good?
Depends.
It depends. Yeah.
what's-
No, I mean, the great thing about a composite is you're not masking the magnetic signal on an MFL running by a corrosion defect. So, I mean, hopefully these composites had some form of marking system to denote the start and end. Probably one of the easiest and
Oh,
quickest
wait.
checks.
Let me go check. Hold on, Tim. Oh, yes. Turns out in my most recent ILI, that's how I got all 100 of them. I can see all the locations of all 100 and the features that they're covering in my most recent inspection.
That's fantastic. What an asset purchase by this operator.
Yeah, well, you know, every now and
Nice
then
job.
a blind squirrel finds a nut. Let's go.
um, yeah, so the primary thing you want to take a look at when you're examining composites on future ILI runs is there any defect growth? So for metal loss, you have both the original ILI run data that you did to select this as a dig and went and excavated. Now you have NDE data. Hopefully all of that is available. You can compare your now current run of ILI data to take a look at what it looks like in reference to those previous findings. So if there is anomaly growth, that's something that you will want to go and potentially take a visual examination on. Is this a composite problem? Is this a tool tolerance problem? Like, is the anomaly growth within tool tolerance? Is it without?
And so you did a great example there in the paper, right? Like you actually rolled an example out in the paper where they went out, thought they had corrosion growth, and it turned out to not be corrosion growth. Right? It was an ILI. All right, so check. All right, so Tim, I'm going to go cut a couple of these out. Give me that breakdown. What does that look like? Now, what do you recommend? Because I get this a lot from operators in the field, and they
How'd
ask
you know
me,
which one to go after?
you know
Like,
what?
and you're lowballing
Here we
corrosion.
go.
What if it was a dent?
Tim, it's
or a crack?
amazing.
Like, we're doing easy.
I just asked.
Like, level up, bro. Here to pass level 1.
Turns out there's a corrosion feature. Let's scenario play here. There's a corrosion feature we think has growth underneath the composite. What do you recommend that we do? Do we just go out there with a saw and cut this thing off? Do you have advice? What should we be doing? How can we use this data point to help with all of the other 99 composites that I'm not excavating?
Yeah, I mean, there is going to be some level of consideration of if you remove the reinforcement, what pressure do you need to be at? So we want to have safe excavation practices, make sure we're not removing a composite that then creates a leak or rupture issue when you remove it at the pressures you're operating at. Once you solve that problem, you're going to want to take a look at, before you start doing any removal whatsoever, just let's take a look at the condition of the composite. Now, composites are, for the most part, vast majority are recoated with some form of coating. So you're going to have to take a look at how that coating happened, what was selected. Can you remove the coating to get a decent examination of the composite? Because the composite, you're going to want to look for any areas of disbondment. You're going to want to look for errors in workmanship. So that's a dry spot in the fiber, that's a wrinkle, an air bubble, anything that could allow some form of moisture to transgress to the pipe and cause that corrosion cell.
Is there a standard process or a document that y'all have that you give to people to do this? Or is it just, hey, send somebody out there, and when Joey gets there, tell him to hit on it with a rubber mallet, and if a rubber mallet goes through the composite, it's bad? I mean, is it, what do we do?
Well, poor Joey, but Yes, there is a document that you can take a look at, and I would recommend asking the composite manufacturer for said document, and it will go through a list of these. This is what a good and a bad composite looks like, and here are some of the acceptance and rejection criteria to determine if it's in good shape. And most of the time, because you're already there, the operator is going to want to take the composite off anyway. So then once you remove it, yes, there's a removal procedure that can be done through, grinding tools, cutting tools. Sandblasting is probably the most prevalent. For that case that you recommended with Atlas, I mean, it's a carbon fiber and epoxy. If you sit there with a high enough grit for long enough, it's eventually going to come off. So
I forgot. I didn't choose carbon fiber intentionally, but it is fun that I chose the carbon fiber one.
So in this process, at all, I'm going to stay on from my last chat, I'm going to stay on my adhesion bandwagon for a minute here and say, because I'm a full confession, I'm pretty ignorant to the composite world in the testing and the installation component. Obviously we know the high level stuff, but is there an element of using a guided wave when you're doing these digs and there's, a previous repair, and I already gave you a clue of kind of where I'm going with this, right? I said adhesion. Is there experience or any work, or what's y'all's position on guided wave?
guided wave is an interesting technology. I would say there's probably not enough work on it to have it as a qualification inspection system. So if you're going to say, I dug up a wrap and I'm putting guided wave on it to see if it's bonded or not,
Yeah,
because of that
that's where I
adhesion
was going with.
mechanism.
I was curious if
There's
there was a sweet spot in the frequency by wall thickness to see if there is sufficient signal attenuation that's like a fingerprint of bonding versus non-bond. And if you hit it from both ways, you could get increased reliability on it. You caught onto that pretty quickly, so that's good. Good job, Tim. So what was your
Thank you.
thought on that again?
No, I don't think there's enough data from enough composite systems to say here's an acceptance and rejection criteria on that to say this is formally bonded or not when you do a
Now let me give you another scenario here. The way, because I wasn't done. So again, I'm playing the operator. Tim, I'm going to actually be cutting out, because we have to do a systematic recoat of about a 1 mile segment. Turns out that 1 mile segment has 3 composite repairs we installed about 20 years ago. Should an operator do anything with that, right? Is there any opportunity to evaluate the effectiveness of that assumption that we operated below the creep regime?
Mhm. Yeah, if you have those design documents and you can take a look at how the composite looks in the ditch, using that 1 mile recoat as an opportunity to examine the quality of the installation visually, then you can kind of take a look at both what's the operational, worst case scenario history up till that point in time. And then after that, what are you expecting moving forward? Assuming that it passes all the quality checks that you're looking at in ditch, we could take another look at that with an engineering analysis and say, this composite, I mean, you can measure the thickness of the composite. If you know that it's an Atlas, you can correlate that to a certain strength. If we know anything regarding installation pressure, or at least assuming a worst case scenario of installation pressure, that can take a look at how the composite's aging and its cyclic fatigue and what it's going to continue to do for cyclic fatigue moving forward. So yeah, there's a lot of post-mortem engineering analysis methods that can be used to help when you combine that with a good visual inspection to extend the life of some of these composites.
So I guess for my second one, has anybody tried to correlate the EMAT data to risk ranking composites? So I'll share here's why, right? So EMAT generates its acoustic wave through the material through magnetostriction. And so one of the things that you can find on the Google search is that EMAT can potentially detect disbonded coating, certain coating types, because it's calibrated to that level of attenuation. So just curious, has that come up yet where anybody's been like, hey, Tim, can I use my EMAT data to tell me which of these composites is still good?
I have not actually had that question yet. You're the first one.
But
I'm going to take that note because I think that'd be fascinating research down the road.
I might poke the bear on that one. That would be a fun paper. So let's poll a bunch of people. That's one paper idea. So poll people on what they think permanency is. and then let's start poking around and see if we can see what, you know, a handful of these signals look like either in guided wave data or in EMAT data, because I think that'd be fun. Again, I'm big on the adhesion part. Again, when I was young, I told you the story. I was like, how are we sure this stuff is sticking? Because I'm using an A and like, this is a big one for me. And I feel like that this composite world, it's all about the adhesion. And so if we could find an indicator to monitor, not even saying assess, right? Because again, I'm thinking permanency, it's part of the pipe. Once it's part of the pipe, I have to manage it. Just look for change. As long as there's no change, we're good to go.
Yep, exactly. But I would love to develop that EMAT technology to be able to see disbondment.
See, if any of the Rosen people and other ILI people that are developing EMAT, see, just hear the podcast. Nuggets for everybody.
All right, Tim, hey, thanks for joining us again. Really appreciate it. Thanks for the good work, too, on looking at it. For all the audience out there, I'd encourage you to take a look at that paper, The Case for the Permanency of Composites, Testing, Analysis, and Case Study. And hopefully we get to hear from you again whenever we want to talk about composites. But thanks for joining us.
You've got my number. Appreciate you having me, guys.
To our audience,
Thanks.
we'll be back in a couple of weeks as we continue discussing with authors from PPIM. Thanks for joining us. This episode of Pipeline Things was filmed at the Workwell. Special thanks to our executive producer, Sarah Etier, my excellent co-host, Christopher De Leon, and our guest from Hinkle, Mr. Tim Malley.